give you my point of view on renormalization. So I think it's a very broad term, and it describes a lot of things. So we have seen this conference even that it means many people, many things for many people. So I don't want to, try to say that this is a one thing and not the other. Some common thread between various notions of renormalization is that it has something to do with singularities, that it's a way to approach the problem of having very singular objects in quantum field theory. So let's say in the approach which I work with, which is Epstein-Glaser renormalization, this is addressed by using some techniques of extending distributions. In other approaches, one first regularizes these very singular objects and then removes that regularization and controls the way in which this has been removed. So yeah, I think now the question, where are we going with renormalization? I think one direction, or maybe just some overarching idea, would be to try to learn from each other and learn about, various techniques, various ideas that are used in other approaches to renormalization, and build more connections, because there are some really interesting mathematical structures in all these approaches. And okay, so since these structures seem to be different on the first side, it would be great to be able to compare them, to connect them. So first of all, to use them to find some interesting physics, to calculate things, to get new conjectures. But also, if these are really seemingly different mathematical objects, which then connect through renormalization, then maybe we can also have something to say for the mathematics. So maybe we can make some interesting conjectures or study some examples by learning from other approaches to renormalization. So I want to think of renormalization as a sort of connection between these various very fascinating branches of mathematics. So a bit of algebra, a bit of analysis, a bit of geometry. This is all coming together via renormalization. Okay, so I think that's my pitch.
Thank you, Kasia. So maybe now Gerald we'll go back to the alphabet. Gerald,
yeah,
I'd like to say a few
words. Thank you. Yeah. So as I said, this is not my natural environment, this conference. You guys are all a lot more mathematical than I am. But I would say that my main motivation is to try and understand quantum field theory from the non-perturbative point of view. So what do I mean by that? We often understand the way we teach renormalization and the way it's often presented is in a natural perturbative framework. Feynman diagrams, Hopf algebra structures, iterative processes for generating a formal perturbative expansion. But we also know that, and you could argue that at one level, renormalization is sort of taking care of the infinities that arise at any given order in perturbation theory. But we also know that there are certain interesting questions that arise when you finally want to resum that perturbative expansion. And we know in certain theories that that process leads to genuine non-perturbative issues that are beyond the formal perturbative structure. So if you then believe that the field theory is defined by its functional integral, so if we know the classical Lagrangian and we can write an appropriate functional integral, you should ask what can we then do? That's a completely undefined object, so we need to do something. So there are many options. You could take the lattice gauge theory point of view and just consider Euclidean quantum field theory. So we've already left physics behind. But that becomes a very interesting mathematical problem, and it's very successful at certain things. You could also take the sort of semi-classical point of view that functional integral is some sort of infinite dimensional exponential integral, and it should be understood in a sort of a saddle point expansion. That's what physicists would call the instanton approach, which is inherently non-perturbative. And that can also answer some questions, but there are also questions that it can't answer. And so the approach I've been considering in the last few years is this resurgence approach, which has at least some promise, although it's not by no means proven, that it can somehow unify these various approaches, the perturbative approach and the saddle point approach. And so there are two natural avenues into this study. One would be to study very high orders of perturbation theory in a quantum field theory. So that's difficult. But in order to do it, this Hopf algebra structure enables, at least in some cases, very high order study of the perturbative series. And so one option is to use that high order information to deduce some non-perturbative information. So that's one approach, which I hinted at in my talk. But there's another approach, is that you can argue that from the functional integral, you generate some infinite set of differential equations, which in some sense you also believe tell you everything about the theory. And then there's this complementary trend series approach, which might be able to encode the corresponding non-perturbative information directly in the renormalized structure of those, let's call them Dyson-Schwinger equations. But now we're also beyond what mathematicians know, because we're talking about some infinite coupled set. But at least you have some context in which you can study these things. And I would like to just mention, one example that I find particularly interesting is something called the Euler-Heisenberg effect of action. If you may know about it or you may not. It's a one-loop QED, but in the background of a constant electromagnetic field. So the propagators become more complicated because they're no longer free propagators, but they're propagators in the presence of a background constant electromagnetic field. But they're known. They're known in closed integral representations. So you can, in principle, do this, and you can study this at one loop and a two loop, and that's all that's really understood. But there's some very beautiful work by Vladimir Ritas in the 1970s and 80s, where he gave an essentially non-perturbative definition of the charge and mass renormalization of QED. And so the charge renormalization was already done by Heisenberg in the mid-30s in this Euler-Heisenberg action. The logarithmic behavior can be seen in this background field calculation. At two-loop, you also have mass renormalization, and Ritas proposed a completely non-perturbative definition of renormalization, of mass renormalization, by arguing that if the background field is electric in character, not magnetic, the QED vacuum is unstable to pair production of electron-positron pairs, and that rate goes something like exponential of minus the mass squared divided by the external field. And Ritas's point was that you can describe mass renormalization by insisting that that mass that appears in the non-perturbative exponent is the renormalized mass. And you can show that that's completely equivalent at that order to the standard interpretation of renormalized mass through Green's functions and whatever by a dispersion relation. But this is an inherently non-perturbative definition of renormalization that has a natural setting in terms of these trend series. And so that's one possibility, that to somehow compare and contrast these perturbative versus non-perturbative definitions of renormalization that I think would be quite interesting. And if I can say one more thing, let me mention that there's a lot of activity in some corners of the mathematical world, and Maxim Kontsevich in particular is investing a lot of effort in understanding to what extent a functional integral can really be expanded in a what we would call a saddle point expansion, which is yet another way of looking at trying to define a path integral, and has a lot to do with this Borel analysis that Mark mentioned and that I mentioned. That's still at the stages of talking about quantum mechanical problems and relatively simple quantum field theories, ones with supersymmetry and special dynamics. But I think it's a promising avenue. And so in that sense, I would echo what Kasia said, is that this is a tough problem and we have to take advantage of any different angle. And speaking from experience, I've spent the last couple of years working very closely with a mathematician, and it's been very productive and very interesting. And I think the more such interactions, it's more likely that we make some sort of progress. So.
Thank you very much. Thank you. So maybe Vincent, would you like to say something now?
In this round table, I have the dubious privilege of being oldest. I think I am also a physicist. So I start with the presentation of the reason as physical roots of renormalisation theory and history of the subject. The late Feynman Dyson once told me he found this theory of renormalization so ad hoc and so awkward that he hopes that another one would be found within 6 months or 1 year. But he is still with us, and for good reasons. I would like to remind you, since most of you are young mathematicians, of the fundamental values that we physicists are attached to quantum field theory and renormalization. It was around the 70s that the standard model of particles and interactions was invented, with one significant exception: gravity. I'll come back later. That revolution could be better called the triumph of renormalization. Weinberg and Salam unified the weak and electromagnetic interaction in the formalism of non-Abelian gauge theory. Then Toft and Fachman proved these theories are renormalizable. Politzer, Gross, and Fitzek developed a theory of this non-Abelian type, QCD, to describe strong interactions, nuclear forces, if you like. And they make the fundamental observations that these theories are asymptotically free, overcoming an objection on the consistency of a quantum field theory raised by Landau. Around this time, Kenneth Wilson enlarged considerably the realm of renormalization under the name of the renormalization group, connecting it with the physical dynamical system. All such names are Nobel Prize winners, testifying of the value that theoretical physicists attach to renormalization. But it was known fact that Nobel Prize in physics must be confirmed by experiments. On the experimental side, the values calculated from renormalized quantum field theory are among the most accurate one calculated from any theory. Take the example of the G factor in a moment magnetic of particles, for example. It is good to anchor oneself in the reality of the physical fact before venturing among the fancy mathematical structure construction of our spirit. From a personal level, I have been fascinated in the recent years by the question, is it quantum gravity, is it renormalizable or not in a certain sense? That is all I want to say, at least for the moment.
Thank you. That's a big question. Thank you. I think now, Bruno, would you like to say something?
If you wish, but I have very few to say, because if you ask me the question, what is renormalization theory, I think I don't know. And so what is its future? I don't know either. So I'm very sorry. But let me just say one thing from the perspective of someone who is more, say, an algebraist. So what I see over the last at least 20, 30 years and a bit more is that there is an increasing interest in, that's the title of your conference, in higher structures. So what are higher structures? Well, let's say in a pedantic way that in the 21st century, people were interested in algebraic structures that were made just of one operation. But it turns out that when you take objects in collections and you take them all together, not one by one, they have more structure. So for instance, you can think at the moduli space of curves and you take all of them, all genus, all mark point, and oh, when you do this, yes, they carry a structure of an operad, for instance. If you take Feynman diagrams, rooted trees, again, if you take them one by one, very few structure. But if you take all of them all together, yes, they carry some structure. So that is exactly what's happening in what I'm seeing in the renormalization theory, but also this comes from algebraic topology. And algebraic topology, in algebraic topology, there was a need of considering these operations in order to faithfully describe the topology, homotopical space, the topology, the homotopy of some space. So, and then when you make this word, you would like to have well-defined mathematical objects. And that's what algebraic topology did for us. It came with notions of infinity algebras, operades. In renormalization theory, we see more Hopf algebras, but if you think at Kohn-Kreimer-Hopf algebra, you look at the generators, they form an operade. So many Hopf algebras come from an operade or a co-operade whatsoever. And even more interesting for me, I mean, recently I've been seeing a few papers in your domain where people are using model categories and infinity categories. So this is absolutely, from my point of view, beautiful and exciting. You see, Sokasha was asking, okay, can we compare algebraic structure? Yeah, sure, that's exactly what operade has been doing for you. You want to compare two categories of algebras. One universal way to do it is you fly a little bit higher, you look at a morphism of an operade, and poof, it compares your categories of algebras with universal and functorial formulas. So at the end, I have no answer to your question, but I have a hope, is that on the one hand, there is algebraic topology and homotopical algebra, which produces formulas like the homotopy transfer theorem with many, many, many counter terms, and they form series. And on the other hand, I see renormalization theory, and my feeling is that, oh, my guys, these are the same. So it is very beautiful to try to understand this. For me, it is difficult because the language is not the same. So we have to talk a lot to understand each other. But I strongly believe that, as usual, when you have two domains quite remote which interact, good can come from both sides. Either a problem on one side raises the creation of an object on the other side, or an object on one side can solve a problem on the other side. So this is extremely exciting for me. And my only comment that I would like to address is, please, 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 don't be afraid of these challenging words whatsoever that are, I don't want to pronounce them, but we have amazingly rich algebraic structures, and they are modeled by actually very, very simple objects. One comment, the definition of an operade, if you may found it, you look at his book. He begins his book by 2 pages of definitions. And I think that is why people were afraid by the notion of an operade. And on the other scale, an operade is just a monoid in a monoidal category. So it is a very simple object. So please don't be afraid by that. If you feel that you are encountering some rich algebraic structure, just ask a specialist, possibly not always me, and then interact with people who know in this domain. I'm sure there is a lot to interact on this kind of domain, of objects. Thank you very much.
Thank you. So there's lots of maths to be done from these ideas. So unfortunately, Lorenzo cannot be here. I don't see him. He warned me that he might not make it. He would have given us another point of view. But I suggest that to open the floor to everybody, to the audience, and
may I briefly comment on what my co-panelists said? Is that okay?
Yes, of course.
So yeah, I found it really inspiring. So I thought I should say a few words about what was said before. So yeah, so maybe first on this perturbative versus non-perturbative story, which I think is a very important challenge. And okay, so from what I've heard from other people's talks, there is usually this way of thinking about this in terms of expansion into Feynman diagrams, which well, we know works well, but there are also other combinatorial structures that are being used. So there are these recent developments with amplitude dihedron and you know, just some alternative expansions like that. So from let's say from my perspective, I guess in perturbative algebraic quantum field theory, we actually tend to work in yet another expansion. So we work in terms of time-ordered products. And I would be really curious to see if the kind of infinite series we are getting from time to time, if they could also be treated by the same methods. Like, can one see this things like resurgence also in that context? So I haven't seen that done at all. So I think it would be interesting to see, because I mean, as Klaus said in his talk, our aim is also non-perturbative. So we have perturbative tools to kind of probe certain aspects of the theory. However, extracting non-perturbative information would definitely be great. So I would like to learn more about, you know, what's being done in other approaches in that regard. Brief comment about quantum gravity. So Vincent mentioned that. Actually, the same week as this conference is happening, there is a renormalization and asymptotic safety conference going on as well. So I do jump back and forth between the two. I want to make a bit of advertising for that, because this is yet another perspective on renormalizability of quantum gravity. So and tensor models play a big role in that as well. So I think the usual speech that quantum gravity is non-renormalizable, we should give up, is maybe a bit too pessimistic. I think we should try to maybe do something there. So I don't know, Vincent, would you like to comment about that, because I know you're also there.
I completely agree with the fact that we should it's non-renormalizable is bullshit. Mais oui. A comment. I would like, beside algebra, analysis, and geometry, there is a place for probability. That's just a comment.
Yes,
and that's what this conference is for stochastic analysis, beyond probability, stochastic analysis. But I was wondering if anybody from stochastic analysis is here, could say, give their point of view, but I don't think Yvain is not here. If anybody would like to say something from the regularity structure point of view?
I can say something. The advertisement of AG Chandra and the like, it seems to me concept like stochastic differential equations, half paths, and the like, bears some striking similarity to the program of constructive theory. Stochastic quantization was developed, introduced by Parisi and Wu, was developed by Jonah Lasigno and Senior in the language which forged almost 40 years ago by Feldman, Magnin, and Senior, and myself. that is Ajay Chandra and Martin Herer was a concept like stochastic differential equations, an analytic BPAZ theorem for a regularity structure seems to me almost striking similarity to the program of constructive theory.
That's interesting. Thank you for this comment. I would just like to add another provocative comment that came out from at least two talks I heard. How different is renormalization from regularization? That came from multi-zeta talks on multi-zeta values, just to throw this into the discussion. Would anyone like to step into the discussion?
Well, I think that there is at least one part where regularization and renormalization are supposed to be very different, is that you have a lot of choice for regularization, right? And that makes you learn very different spaces. While if life is good, renormalization should be unique. The renormalized value should be unique.
No, I don't agree with that. I think, well, okay, first of all, I think renormalization and regularization are really different things. So regularization is to kind of make things finite and make it possible to, let's say, multiply them, extend them, or whatever you want to do with them. Renormalization is about extracting physical information. So renormalized quantities should be the physical guys that you want to measure and compare with the universe, which doesn't say there has to be a unique answer. I mean, these could be, free parameters that you measure in your theory, and the value for that parameter is fixed by, your observations. So renormalization group as such is acting on, it transforms renormalized quantities to each other. So renormalization group is essentially describing the ambiguity you have in renormalization in finding these these physical values. So
okay, but at least if they describe physical reality and you bet that this one thing exists, it should be something. Of course, up to what experience you're precisely doing, but you're not, like, you can renormalize two very different things in very different ways, have very different objects, and at the end still coincide on the renormalized value. If you are doing the same things at the same scale and everything else coincides, right?
Well,
that's just what.
Well, yeah, I mean, David, I think, has something to say from what I see.
David, please. Yes.
Okay.
Intact.
Can I speak? I'm very much on the side of Kasia and Vincent here. See, I'm rather older than you. The year before Vincent was born in 1954, Gell-Mann and Lowe wrote this paper, which I read as a soissons retard in '68. And it said this absolutely shocking, terrifying thing, that when you write down a quantum field theory, for each and every one of the terms you write down, you don't know what you're talking about. And that has to come from experiment. And renormalization is the process that we have to do if we're living in such a world. And at least order by order in perturbation theory, it makes absolutely precise and unambiguous statements about relationships between physical quantities, between measurements. It makes ambiguous statements about the relationship between experiment and what you wrote down on a piece of paper, and that's the fault of your piece of paper and not of the world. So I would say that, and we've seen that the Sender model uses all and only those theories which are renormalizable in that strict sense in 4 dimensions. So I would say to mathematicians who hear that, if you have some equation that you write down and you got some parameter and some coupling constant down there, and someone asks you, what is it? then you're not in the world that we do. We live in a world in which every single thing we write down on a piece of paper has no relationship to measurable quantities. Any human endeavor of that character may touch on some of the richness of renormalization.
So mathematicians are also allowed to say something. So I think we've seen lots of maths emerging from renormalization, or motivated, triggered by ideas coming from renormalization. Does anyone want to say something about the potentialities that were also mentioned by Kasia before?
I would like to take some provocative stance. In fact, you never should renormalize. The only thing which exists is a renormalization group. The infinities, the regularization, you could simply get rid of them, simply saying that you should not compute infinite things. So what it does say, it's if something is infinite, in fact, you should only look at its variation, which with respect to a scale generally, which will make it convergent. So it's maybe in some sense it's not completely contradictory. And I remember having done computation for a cousin, which is a physicist, where the trick was to decompose some perfectly finite quantity into a sum of divergent one, and each divergent one was trivial to evaluate. And so the idea of renormalization maybe is the power of being able to decompose something in parts which individually do not make sense. But in the end, physically, what you are really looking at is the difference between quantities, so that by taking the difference, the divergence have gone away. But maybe it's a little too strong a statement. But
so you view it as a relative thing. So
it's linked to the Bogolubov method, where you simply take derivatives of your green function up to the point where the function becomes convergent. It's not always sufficient, because if you have subdivergences, you cannot reach the subdivergence in this way. But in a sense, what I've done with Schwinger-Dyson equation push me to think that the less infinities you allow in, the better you are. if you cannot be too afraid of involving infinities, it's this simple case where you have sin square over x squared. If you decompose your sin in the exponential, you have divergent things, but it's the way to go.
Thank you. Who else would like to say something to react to what has been said up to now?
Sorry, may I react to Mark? So I agree. One shouldn't compute things that are infinite because, you know, that's a lot of work for nothing. It's all infinite. But I think there are different answers to that. So the problem with having subdivergences is actually an important one. And okay, so I would say, okay, well, I'm trying not to, you know, compute infinite things myself. But I have a different viewpoint on this question. So I'm okay with computing things that end up being well-defined and finite, but not necessarily unique. So my problem, you know, when I compute something is to find a structure, find you know, an answer to a question which doesn't always end up as a unique one. This is this problem of renormalization group acting on things. So that I actually feel it's maybe an intrinsic property of the world, as David said. And maybe this is just how things are, that there is the renormalization group. But yeah, I mean, of course, one has to, I think one has to avoid unnecessary infinities. So if you have this sort of approach to life that, oh, quantum field theory, it's not well defined anyway, so we can stick infinities left and right and nobody notices. Well, this is no good, right? So yeah, I think it's important to use the combinatorial structures and, you know, understanding of the analytic structures as well to really, you know, present the problem in the most sensible and efficient way. So sometimes these infinities are just not there. So yeah, I think that's a good lesson.
Kaja, sorry, I have a small question for you.
Hi, Dominic.
You spoke about non-uniqueness when you compute finite things after renormalization.
Yes.
What is your interpretation of this non-uniqueness?
Well, yeah, so this, I mean, in the very physicsy way of putting things, I mean, these are the counter terms in your renormalized action, so, or renormalized observable. So you end up with, you know, the answer to your question, which is unique up to, mathematically up to adding some combinations of Dirac delta and its derivatives. And these coefficients are then free parameters that you can fix. So this is essentially the philosophy in Epstein-Glaser renormalization, that you can, you know, you can compute your time-ordered product, but there is ambiguity in doing so, which is then expressed by adding local counter terms. So these can actually be then physically interpreted in terms of these parameters that you can measure. So yeah, and mathematically, well, you know, you multiply distributions with certain scaling degree, and hey, you know, you have this and that many parameters to fix, and that's life. Life is brutal.
Let me ask a question. Is our need to renormalize just a result of us being clumsy and not being able to do better? Is our aim to get rid of having to renormalize?
No, I think David should say something about it.
We'll be jobless if we do that.
Oh, David, you're muted.
Yeah.
Oh, yeah.
If you don't need to renormalize, you shouldn't be at this conference.
No, I'm saying going beyond that. And I mean, it looks as though, you know, we're going through a lot of trouble to deal with divergences that we don't really understand. Is there any hope that, you know, we can incorporate all that in one big machine that then we wouldn't have to do this messy stuff.
Well, I mean, you can always improve your tools, right? I mean, ideally, you know, I would say mathematical understanding of renormalization shouldn't remove renormalization from the game, but should allow us to build this machinery you said that will, will be the optimal way of dealing with the problem, right? So, yeah, I mean, this is what we are here for. We want to understand.
Yes, yes, and I shouldn't be raising this question as a
controversy is good.
But I really feel something like that, you know, that we're doing that because we can't do better, but could we somehow get rid of this problem and go well beyond?
Maybe can I suggest an analogy for mathematicians? If you're looking at roots of polynomials, it is a fact that you have some symmetries for them, which is the Galois group. And I would have a question for people who actually know physics. Is this an actual relevant analogy to compare Galois groups with a renormalization group, or is it complete?
Yes, there's Pierre Cartier's cosmic Galois group. Yes, indeed. People are looking for a group that could encompass all these ways of going from one renormalization method to another.
May I ask another question in that direction? We've seen recently in math that the notion of group was too restrictive. So I'm thinking in the following direction. You know Lie theory. Lie theory, you have Lie algebra, which integrates into Lie group. And you use that and you love that because when you're doing deformation theory, your deformation problems are encoded by Maurer-Cartan elements in Lie algebra. And the action of your gauge group tells you exactly how you can perturb your guys, your structure. But it turns out that many deformation problems cannot, I'm being a bit provocative here, but there's a precise meaning behind my statement. There are many deformation problems where you need an homotopy Lie algebra. So where you have to take, and this is exactly this passage from a finite equation with two terms, quadratic, to an infinite series of. So this infinite Maurer-Cartan equation has infinitely many terms. Okay, fair enough. So now you have a deformation problem. It is encoded by an L-infinity algebra. Maurer-Cartan elements make sense there. Okay. And then, oh, but how can I compare Maurer-Cartan elements? Because now, how do I integrate an L-infinity algebra? It does not satisfy anymore the Jacobi relation. So what is the good notion of a group? But there is no. And there is a notion of infinity groupoid, whatsoever you want. So have any of you encountered this kind of guys? Or because the words I'm hearing right now is Hopf algebra, is groups, but there are higher generalizations of that, which do a quite good job, I would say.
So I would say, well, L infinity definitely appears. A infinity, groupoids are definitely there. Infinity groupoids, that's probably not my cup of tea, but okay.
Okay, I'll explain to you. It's easy.
Actually, I wanted to say something about the operands because you're advertising operands and this is great. So I see operands everywhere. So
Me too.
You know, look, they're operand. So in actually, you know, in algebraic quantum field theory, there are at least two now like ideas of how to use operands to you know, describe things. So there is this work of Schenkel about the colored operand for a QFT, and there is this work of Eli Hawkins also about the formation of diagrams of algebras in terms of a certain operand. So there are operands on the market. I think, I think this is a good way of thinking about these things. So yeah, more operands.
That's exactly what I was saying. I mean, the operand structure pops up as soon as you start considering guys in collections. If you consider elements alone, no. But if you have guys labeled by integers, you know, one or several for each integer, I don't know, you take rooted trees with n vertices and you take all of them, there is strong chance that you have an operatic structure there. I'm not advertising that to sell any book, etc. That's not what I'm saying. But I'm just saying that considering the operatic structure on collections reveals their internal structure. That is why it's extremely useful.
Let me ask Jim. He's been asked by David whether you would like to say something, Jim?
Well, I was not in on the whole discussion, so I don't know about the transition from renormalization to operads, but certainly operads and particularly L-infinity algebras seem to be all over the place in pseudo-mathematical physics. So I would be delighted to hear more about where people think this is going. Damien or Kasia or Bruno?
Yeah, so I guess, well, you know what's my corner of the woods. So, I mean, these are definitely present in the PV formalism. And yeah, I think that's, yeah, I mean, there are, okay, so there's more abstract side and there is more practical side of things. So there are currently some new developments about also doing BV formalism in theories with boundary. So then you also have higher structures. So you have yeah, more interesting mathematical relations. So I would say that this is where the movement is at the moment, trying to understand things with boundaries. It's a bit like in topological field theories, but you want to use that philosophy also more generally.
Yeah, it's more precision to the relation to the mathematical physics. I have a deprived childhood. I didn't learn physics when I was young.
So if I may, for those of you who don't know what we mean by operad, we mean operad in a very relaxed and wide sense. I mean, and this is what we should do. I mean, do not necessarily consider the definition of an operad. We have operatic objects. So there are props, there are colored operads, there are properads, there are many guys. So first, don't be afraid by the definition, please. And then be very open-minded. You have a guy, ask yourself what kind of algebraic structure it satisfies. Maybe it has operations with 10 inputs, 12 outputs, some loops. Good, we have the guys for you. And if we don't, we're going to coin the good definition. So over the last, what should I say, Jim? At least 60 years or something like that, there were an increasingly amount of operatic structures that were found. And so operad models operations with several inputs and one output. Colored operads model operations on several inputs, one output, but that can act on many different underlying space. Wheeled props take care of traces, etc., etc., etc. So we have this, and it still needs to be developed.
A question out of left field. Have any of you looked at the embedding tensor and the tensor hierarchies? No. It's very frustrating. They're written by physicists of the indicial type.
Understood.
Difficult to read. And I think Vincent is not here anymore. Is he there? He could maybe. Yes. Yeah. Would you like to react to that?
Oui. Now that supersymmetry and superstring theory is no longer the unsurpassable horizon of physics, we can, with renewed energy, get down some basic problems, and among these, as see the most promising one, renormalisation. I take comfort with the idea that matrix theory are asymptotically safe and tensor theory are asymptotically free. Someone would construct this. This is much simplification compared to non-abelian theory. There are no gauge fixing.
Thank you.